Hi, how are you?
I'm good.
What year are you?
I'm a freshman.
Awesome. And what's your major?
I'm biology.
Ah, okay.
Yeah.
This is a little bit of a different topic, but we do work with the hospital, so maybe.
Yeah. No, I'm also interested in environmental science too. So I definitely did want to stop by.
Awesome. Okay, I think maybe at 2:17, or do you want to start now?
You can do 217.
Okay. How are you liking, how has it been to start your year during this time?
It's been pretty good. I got to join Verse, which is really awesome. I really like
Mhm.
Verse, and Isha's actually like someone I work with a lot because we edit for Scientia. So it's super cool. And I've been making a lot of good friends in this club and just like outside of the club as well. And I really like it.
Cool. Wow, that's really good that you got involved with kind of on your in the science side so soon.
Yeah.
And what about y'all? What year are y'all? I see dorm, so freshman. Awesome. Oh, I remember when I was freshman. I feel like it was just yesterday, but I'm graduating in December. So awesome. I'll go ahead and get started. Let me just, sorry, I have two monitors, so I have to make sure everything's. Okay. Awesome. So my name is Gabriela Fierro. I'm an environmental science student, but I do have minors in entrepreneurship and corporate innovation and political science, but I'm more interested in the sciences. So I worked with a little bit of a collaboration with the Department of Electrical and Computer Engineering and the Department of Mechanical Engineering to design an energy grid. And the whole reason we did this was to increase energy access in developing countries. So we use swarm electrification, which just means that you build energy systems very small scale in many little pieces, and then you connect them all. So this is something that's more cost effective. Awesome. So I'm going to talk through the significance, why does it matter, the challenges modeling a system like this, figuring out the cost, and finding a final architecture, and also the next steps for the research. So why does energy access matter? It becomes pretty obvious whenever we think about all the technologies in our hospitals that need to get powered. How we learn. Right now we're using a laptop, right? Or a different type of computer. How we communicate, prepare our food, travel from place to place, build our cities, conduct agricultural practices, pass on information, pay for things, entertain ourselves, and even refrigerate our food. So all of these things are electrically dependent. So we also asked, is there a relationship between human development and how much electricity you consume? So we found the answer to be yes. So here you'll see other countries that rank closely to Haiti in terms of the human development index. So Haiti is the place where our design is getting built. And so these countries just allow for a spectrum of applicability. So where else can a system like this be built or be possibly beneficial? So where is Haiti? It is right here sharing an island with the Dominican Republic. And if you look up north, that little blue tack that says I to D, that is where our 4-phase development plan of an energy system is going to be. And I to D is just the name of the hospital that is our partner that kind of said we want solar panels and we want to bring energy to the surrounding community. So the challenges, what are they? We found them to be fuel dependence. So a large portion of their GDP is diverted to external sources. That's something that can be invested from within, inside the country to maybe improve infrastructure or other things. So also price volatility. So the price of fuel is never constant. Political conflict or scarcity, all those things just make it fluctuate so much. To where people like to argue that renewables are just not as reliable, or they fluctuate, they're intermittent, and that fuel is just better. But whenever you look at price and all of those scarcity and conflicts, scarcity and political conflicts, it actually makes other energies more competitive. So political instability, Haiti has a lot of political turmoil. The national utility is not supplying energy. If you touch those power lines that are already there, you won't get electrocuted. And although that sounds good, it's a bad sign. So this highlighted the importance of civilian solidarity. So people see that their government is not providing for them. So they say, okay, what else can we do? Also, natural disaster. This is a place of a lot of hurricanes, a lot of flooding. So how do we build a system that can withstand those storms? And also theft and non-payment. Again, this is a developing region. People have priorities of feeding their families and other things that go before paying their utility bill. So I want to make sure that we understand what type of theft I'm talking about. People are not stealing solar panels or other equipment because they want those things there. What they're doing is they're diverting this flow of electricity to another household. And that's dangerous. A lot of people die from this because they're inserting needles into the lines, and that can be really dangerous. You can easily get electrocuted. So this is something that's hard to detect too, because there's so much energy going through these lines that small amount is really hard to find. So what resources are available? We thought about fuel, again, just not cost effective. And then we thought about hydropower. But the problem is that the hydro systems are really large and they require a lot of upfront costs. And also toxic materials build up behind the dams. And whenever you tear those down, eventually you allow all those toxic materials to flow into the stream and affect the health of the residents of the community that you're trying to help. Wind energy, also not viable. So we decided on solar. So we mapped here the GHI, that's just a measure of how much solar energy is possible there. So we found that the sites with the lowest potential were still prime candidates for solar photovoltaics. And also, again, if we want to electrify in a modular way, then this is what supports that swarm electrification, building small pieces and then connecting them all together. So this is just a map of the development phases that I mentioned. So you'll see those beige polygons to the left and the right. So those are systems that are already built. They're mainly diesel based with a little bit of solar. And then that polygon to the north that I'll zoom into, this is the one that I designed for. So this is 200 residents that will be receiving energy through solar panels. And COVID didn't let us conduct a couple of surveys to figure out exactly how many people, kind of get those nitty-gritty numbers. So we had to use just these maps and other software to figure that out. So here you'll see load profile. That's the next step in modeling the system. So people groups have certain patterns of using energy. So you get home, your parents get home, maybe at 5 o'clock typically, or 4, whatever time you get home from work, and you flip on the lights, you flip on the TV, maybe start washing something, maybe you turn on all these appliances, and that makes a peak of your usage happen in the late evening. So that's dependent on your lifestyle or the American lifestyle or whatever community that you're living in. And that differs from industry or commercial areas, and maybe a building needs to have their lights on all the time or wants to have their lights on all the time. So that pattern is figured out with Homer. So it's the hybrid optimization of multiple energy resources. So it's an awesome software that lets you see right here what the profile is. Also, what is the chemistry of your battery? What are the different lines that you could use? What is the voltage that it could carry? So really specific things that we can plug in our appliance-based calculations into the system. So this is just zooming in to the software. What does it look like? So you can see here up at the top, you can put in a wind turbine, a generator, another battery, a converter. And it's interesting because right now a lot of batteries are coming out with different chemical makeup. So what we used was lithium ion. What my advisor wants to use is a flow battery based on iron, but there's also sulfur and magnesium and other types of batteries that are up and coming. So also the cost. So we found that the project lifetime was about 25 years, which is normal. But also when you look at that annual capacity shortage, 10% is pretty high, especially if you compare that to us living in the United States where energy is pretty constant. Sorry about my dog. So that just means the percentage of time that we cannot provide the electricity that this community needs. So although that's pretty high, we have to take into account that these people currently do not have any electricity. So we'll only work on kind of closing that gap, closing that 10%. And again, a solar architecture won because of those price spikes that go from a little upwards of $2 a gallon to up to $9 a gallon, where the lines for the gas stations are ridiculously long and there's scarcity and no one can afford fuel. So here you'll see the cost is pretty big. And we were like, why is it so big? And we found that it was because of the battery. Although we were purchasing it locally, it was not being manufactured locally. It was actually being manufactured in California. So that leads to a large cost. So we started asking, how do we make sure that our projects invest in a local economy and local manufacturing, or that we bring a battery that people can make in their garages? So this is the previous architecture. Don't worry about understanding this. That's just the battery, solar panels, the generator, and the site. And also a converter that just makes sure that the power being produced by the panels is converted into a power that's compatible with your refrigerator or your TV or whatever else, other appliances you want to have. So the resulting schematic was this. So you'll see DG means distributed generation, those are your solar panels. Lithium ion is the battery type, that converter again, and all to supply a system that is based on a 50.66 kilowatt hours per day load, accounting for a peak in energy need of 7.32 kilowatts. So again, this is a project that's ongoing. 2 phases have been built. The third will hopefully be built soon if COVID allows, and we'll be moving on to that polygon to the south, that phase 4. But thank you so much for listening. Thank you to Burst. Thank you to the Baylor McNair program that funded this research, and Just Energy, which is the company owned by my advisor.
Awesome. Does anyone have any questions for Gabriela?
So when is like the expected, like when will this all be like kind of done? Like at least this phase of the project?
Yeah, so that's a good question. It was projected for this year, by end of year, but the problem is that travel is prohibited right now there, and also the political, it really depends on what's going on in the country, right? Because in January, for example, when my advisor wanted to travel there, we couldn't because people were rioting. There was a lot of, it wasn't safe to go. So it really depends, but we have the funding now. So as soon as the political climate in the country allows, and as soon as COVID kind of calms, or we can figure out a protocol to make sure that we can, because we have workers there that are electricians, they're welders, right? Because we're trying to invest in the local economy. So we want to make sure we don't bring anything there, and also that we don't bring anything back. So the answer is it depends.
Okay, cool. So we're gonna quickly take a picture. So can everyone just do the SICM really quick? Cool. Okay, 1 second. 1, 2, 3. Okay. And can you guys see the chat, or should I send the link for the form again? I'm just gonna send it again, I'm not sure. And that should be your last poster presentation, so you guys can head to a breakout room, and the links are on the Burst website. Yeah, but you guys are good to go.
Awesome. Thanks for having me.
Thank you.